So our discussion of recursion leads us to what's called the master theorem, or the master theorem of divide and conquer, something that tends to be very useful mostly because a lot of recursive code has a very common template or formula to it. And so it turns out that smarter people than I have come up with a way that you can very quickly take a piece of code that follows a certain format and directly compute a closed form, specifically for its big O complexity. Now, before we can dive into that, we need to review a little bit on function forms. So recall that what's a closed form? It's anything you can directly compute. So I can say f of n is n times n plus 1 over 2, and as long as I know n, I can immediately just give you a value for this. A recursive form is one that relies on the recursive function itself in order to determine what it is. So I could say a recursive form could be f of 0 is 0, f of n is f of n minus 1 plus n. And this is recursive because I don't know what f of n minus 1 is. I can't compute it directly. Closed form is really helpful when we're looking at big O, omega, theta. Recursive form, not super helpful. So you need to be able to convert recursive formulas into closed form to be able to do this work. And we know how to do that now, although it can be very tedious sometimes. I'm blocking letters. There we go. Okay. Again, a little bit of review looking at recursive runtime. So here's our formula. Our function, it computes a factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. So if n is 1, well, n factorial, 1 factorial is 1. And if it's anything else, then it's just the number itself times the factorial of everything below. In other words, 5 factorial, for instance, is equal to 5 times 4 factorial, which should, I hope, make sense to you. What is the runtime of this? Well, we need to look at the base case and get the runtime of that. Then for the recursive calls, get the runtime in terms of how big the recursive calls are. So for the base case where n is 1, we have some constant amount of work. We'll say c. If you said 1, it would be fine too. For the recursive call, we say that it's t of n minus 1 plus d. Why is it d? There's still some constant amount of work that had to go into figuring out to get there. We had to do a comparison and such. So the time spent on the factorial is the t of n minus 1, and there's some constant amount of work that we say is equal to d. Now, given that, here's a practice question that we'll talk about in class. What is t of n in terms of big theta? Is big theta of 1, log n, and n squared, or none of the above? Well, turns out I'm going to spoil it for you. And so if you're one of these cool people who are watching my videos, you're going to know the right answer for class. And everybody else will look foolish when they don't have the right answer because they neglected to watch these videos they're supposed to watch. Let's prove it formally. We want to look at the base case, get the runtime of that, look at the recursive calls, get their runtime, and then move forward from there. So base case is constant, so we'll have t of 1 is c. Recursive calls, we have t of n minus 1 plus d, where d is some constant. Okay, so altogether, we can declare our recurrence to be equal to this. C, where n is 1, and t of n minus 1 plus d, where n is greater than 1. And this is a recursively defined function, not a closed form, so we need to do some more work from here. So how do we figure out what a closed form might be? We follow our 5-step process. First off, repeat substitution. We look at each iteration. So k is 1, we have t of n minus 1 plus d. K is 2. If you put everything through, we get t of n minus 2 plus d. For 3, t of n minus 3 plus 3d. This doesn't look too complicated, so we're going to guess that it's t of n minus k plus kd for the kth iteration. So given that, we're going to solve for having n minus k equal to our base case, which in this case is 1. So n minus k is 1, we get k is n minus 1. We plug that into what our guess is, which means we get t of 1 here, and we get n minus 1 instead of k, which gives us t of 1, n minus 1 times d. So we get c plus n minus 1 times d. We put the d inside the brackets, and we end up with what's here. This is a potential closed form, and you should try doing the proof yourself. Show that this closed form is equal to this for all natural n. So we say that this recursive algorithm has worst case runtime of dn plus c minus d, which is in big theta of n. You see n is the biggest term here. And we know already from week 4 of this class how to formally prove that as well, showing it's in big O and big omega. So you can be this fancy fellow from back in the early 2000s or late 2000s, was it? Who can confidently declare that it is a big theta of n algorithm. All right, another practice question we'll talk about in class. Which of these is faster? Here is code that computes a factorial. Here is code that computes a factorial. Which one's quicker? Now, here's a very common sequence / formula that a lot of people like to talk about in math and computer science, which is Fibonacci. So the Fibonacci sequence is pretty straightforward. Any given Fibonacci number is the sum of the previous Fibonacci number and the one 2 steps before that, where the first 2 are 0 and 1. So they are in order 0, 1, 1, 2, 3, 5, 8, 13, and so on. So here is a very simple piece of code that computes it. If n is less than or equal to 1, it's just n. Otherwise, it is the sum of the previous 2. Very, very short. Now, given that code, let's suppose s of n is the recursive function where it's c if n is less than or equal to 1, and it's s of n minus 1 plus s of n minus 2 where n is greater than 1. And t of n is where t of n is c, where n is less than or equal to 1. And t of n is t of n minus 1 plus t of n minus 2 plus d, for n greater than 1. Is s of n correct for Fibonacci? Is t of n correct for Fibonacci? Are neither of them correct for Fibonacci? Which is correct? Another Fibonacci question. What is it in big theta of? Is it big theta of 1, n squared, 2 to the n, none of these? So I'm going to spoil this one a little bit for you as well. Or at the very least, maybe I'll just give you something to think about, which is if you are trying to calculate, let's say Fibonacci number, the fifth Fibonacci number, right? How do you calculate the fifth Fibonacci number? Well, to do so, you need to calculate the fourth and the third, right? And how do you calculate each of those? Well, to calculate the third, you need to calculate the second and the first. And to calculate, now the first you can do directly. To calculate the second one, you need to do the first and the 0th. To calculate the fourth, you need 3 and 2, and so on and so forth. You can kind of see we're building a tree here, right? We can see that some of these levels are going to be full, some of them are not. And if we really mostly just care about the full levels, it's not really too hard to see that the number of levels here that we go through is n over 2. So perhaps that is something that might help you think a little bit about what is the complexity of this going to be in terms of big theta. So if you need to figure out recursive runtime, what do you do? Well, here's what we know so far. We can state t of n, the worst case runtime for input size n, this being a recurrence, find a closed form for it, which we found out the previous week, and then find a theta bound from that closed form using what we learned in week 4. But that's probably a lot of work, and I'm sure at this point you've already seen it's a lot of work. So here's another way that we do it. We skip through a lot of the beginning just by guessing what the theta bound is. Whether it's through intuition, we think we might know, we've seen something similar before, we just trial and error it, etc. And then just straight use induction to prove the bound. Maybe you should try it yourself. Maybe consider coming up with a recurrence that looks sort of similar to some of the ones we've seen before and see if you can just guess what the theta bound is and then do the proof. If you can, it definitely saves you a lot of work. So here's a proof I'm not going to speak all the way through. You can hopefully see it at least on the slide here. If it's a little blurry, perhaps I can post it elsewhere for your convenience. At least I guess if you download these slides, you can see it. And there are 4 possibilities that we'll go over in class. Either the base case is wrong, there's an error where there's the star marked over here, there's an error before where the star is marked, or this is a valid proof. You tell me. Same options again for a slightly different proof. Here it is. You can take a read, see if you can figure it out. So this brings us to the master theorem, a very, very super fast way to get one of the bounds on a recurrence. So This only applies to a very specific format of recurrence, which needs to look like the following. A, which is a constant greater or equal to 1, times t of n over b, n being the input size and b being a number greater than 1. It cannot be equal to 1 or it's smaller, or you have weird stuff going on, plus something that is a function that is big theta of n to the k, where k is greater than or equal to 0. So this specifically generally needs to be a polynomial, otherwise the master theorem does not apply. If you have a recurrence that is in this form, there is a theorem that says you can conclude the following about the asymptotic complexity. If k is equal to log base b of a, then your recurrence is in big O of n to the k times log of n. If k is less than log base b of a, then your recurrence is in big O of n to the log base b of a. If k is greater than log base b of a, then your recurrence is in just straight big O of n to the k. Now, it's probably worth talking about, how exactly does this all come about? In, I think, the next slide, maybe it will suggest you try to prove this yourself, but I do want to at least break down where some of this is coming from. So generally when we see, the reason that this is sometimes a very common recurrence formula is that the first half of this often refers to the size of subproblems that are being solved. So when you think of something like, let's say we're doing a binary search, right? With a binary search, you're splitting up the list that you're looking through until you can find the right spot. And so in a binary search, we could probably easily say that the first part here is 1 for A, t of n over 2, so b being 2, right? Plus, what happens after that? Well, the only real work you need to do in a binary search is just checking an element. So usually this is just a constant amount. So a constant amount is in big theta of n to the 0, which is constant time. So what do we have from that? Well, we have k is 0, a is 1, b is 2. Let's look at what we have here then. K is equal to log base b of a. Well, if we plug in the numbers, what do we get? So we got k is 0. Log base 2 of 1, well, 2 to the 0 gives us 1. So that actually is the correct option, is option number 1. Which means that our code is of big O of n to the 0, which is 1, log n. And actually we already know that, at least hopefully we've seen by this point, that binary search is a big O log n function. So hopefully you can at least buy that part of the argument. Now, what about these other scenarios? Basically, the way that the master theorem works is that it tries to sort of ask the question of which is more significant, the work of trying to deal with the breaking down of all the sub-problems here, whether it's splitting the list in half or so on, or the work of combining all of that together. And we'll see in the next lecture how to actually do the coding for this. But for right now, the master theorem is really just asking you which is going to be a bigger deal. Is it going to be this term over here, this polynomial, in which case you end up with big O of n to the k, or is it going to be the work that's done over here, in which case you have big O of n to the log base b of a? So let's take a look at a couple of examples of this just from the sort of math side of things. Just given an arbitrary formula, t 2t n over 2 plus n. What do we have here? A is 2, b is 2, k is 1, log base 2 of 2 is 1, which is k, which is the first case. So we have that t of n is O of n log n, and we have n log n this time because it's n to the power of 1. Okay, next option, 2t n over 3 plus root n. So what do we have here? A is 2, b is 3, k is 0.5, this is a square root. And bear in mind, these don't have to be integers, right? K can definitely be a fraction, that's fine. Now, log base 2 of 3 is bigger than a half. So this term is actually larger, which means we have the second case. K is smaller than log base b of a. So that means that the runtime of this would be t of n is big O of n to the log base 2 of 3, which is, 0.5 something. Okay, here was the slide I was mentioning moments ago, which is, something that you can try for yourself. And the reason I suggest you try this for yourself is, first off, because it's a good practice in case you're not super comfortable with doing repeated substitution, being able to do this on your own means you can probably convince yourself you are I forgot this character's name from Kung Fu Panda, at doing repeated substitution. Also, if you get stuck, there are like a million different solutions out there that you can look up for how to do this, which is something that can help you if you get stuck at a certain spot. I recommend you don't look up the answer to how to do it, but if you get stuck at a certain spot, you can perhaps look at what you might need to do to move on to the next step from there. And being able to do this means you really understand repeated substitution and the master theorem itself as well. So definitely worth doing. Not something that I will provide to you because I think it's worth your time to give it a shot. So now that we have this master theorem, how do we use it? So the first thing you have to do anytime that you're going to apply the master theorem is to study the code. You need to know exactly what the recurrence is that emanates from the code that you have. Make sure that that is in the form of a times t of n over b plus f of n, where f of n is in big theta of n to the k. And a must be natural, greater than or equal to 1. B must be greater than 1, but that's it. Real numbers are fine. A is the only thing here that has to be a natural number. And k for greater than or equal to 0 can also be a real number. That's totally fine. Once you have all that, apply the master theorem. That gives you a big O bound. Now, if you need to do big theta, you still are going to have to do the normal means like induction to show a big omega bound. But if you have big O and big omega, you can decide, is this big theta of something or are they separate and therefore there is no big theta. So more practice problems we'll go over in class. Here is binary search. Is binary search big theta of log n, big theta of n, big theta of n log n, or big theta of n squared, or none of the above? I think I actually mentioned the answer earlier in this video, but, not everybody I think will watch the video, so you can feel smart by remembering what I said, or figuring out for yourself what the answer is. Here is a former test question, which we'll also talk about in class. Consider this recursive function from all the following, which are correct statements. And there are 5 statements here. You can read them, I think. We'll talk about what the answer is. Here is another example. Can we apply the master theorem to Tn is 2 times t of n over 5 plus log base 2 of n plus n to the log base 2 of 3. And for the case of keeping the math simple, we're just going to assume that n is going to be a power of 5 to make it so breaking this down is a little bit easier. And the base case here is t of 1 is 1. So which of the following are true? Think about it a little bit and we'll talk about it.